In this talk, I'll go over a method to solve synchronized multi-arm rearrangement using mode graphs with capacity constraints. I'm Rahul Shome. I'm a postdoctoral research associate at Rice University, and this was work done while I was at Rutgers University along with my collaborator Kostas Bekris. Now, synchronized multi-arm rearrangement is an interesting interface with compelling needs in automation and robotic technologies, where you might have scenarios where multiple robotic arms are available to your disposal. Take, for example, robotic assembly floors of waste management or sorting and order fulfillment. When you have a lot of robots available to you for doing manipulation tasks, if we can figure out a way to make these robots collaborate, we can address a much richer class of tasks in the same workspace. For instance, making stationary robots collaborate and coordinate with each other immediately increases the reachability of the robotic arms, as can be seen in this video. So you see an array of 9 KUKA manipulators which are moving around objects in the workspace and are reaching much beyond their own reachable workspace by handing off the object to other arms and thereby extending the reachability. And the idea is, in this work, we focus on multi-arm rearrangement where only the object poses need to be changed using the manipulators, and we want to address the scalability issues and the computational challenges in trying to efficiently come up with solutions in this problem domain. Because to find efficient solutions, you have to, for instance, in this case, reason about, just in terms of the robotic degrees of freedom, 63 dimensions. And on top of that, you have to reason about all the possible choices of actions you have, which again blows up the search space. So addressing this kind of problem gives us an opportunity of applying efficient techniques for interesting robotic coordinated task planning. So what does the model of our problem look like? So first of all, object rearrangement involves changing the initial poses of a set of objects to their respective target poses. We affect that change using manipulators that can perform pick actions, place actions, and handoffs. And the validity of these actions depend upon the reachability of the manipulators and their corresponding pairwise interactions. Now, at what instance of time the robots can perform these actions is limited by our synchronization assumptions, which forces these actions to be executed at synchronized time steps instead of any arbitrary instance of time. In order to identify a class of problems where we can argue the existence of efficient solutions in this domain, we choose to focus on monotone instances in our evaluations to study the effect of the combinatorial explosion of all the available choices of robots, actions, and objects. Monotone problems imply that an object can be transferred to its target location using a single grasp. Even under this assumption, we will have to contend with an efficient way to narrow down the search. Moreover, it is important to point out that in our demonstrations, we have actually shown that there exists a class of non-monotone problems, which we can also address, where it might be necessary to grasp an object multiple times. And I would like to point out that the class of problems that is represented in this work, even for very small problem instances, is not trivial, as can be seen in the figure on the top right. So in this situation, the problem involves the task of just switching the objects on the tables, right? And it turns out that if you have to do this greedily so that both robots go to pick up the corresponding objects in front of them, then there is no next action that makes progress in the task, because a handoff is no longer possible. So even in such a simple scenario, the solution requires careful reasoning about the consequences of committing a resource, or in this case the arm, to an action, so that it does not block a future action. So this level of task planning by itself is an interesting computational challenge. And we need to find effective solutions which are not naive and greedy. So one way to think of it is we look at all possible task modes or all possible things that the robot object system can be in. It turns out that this space quickly gets too large to explore in an exhaustive fashion, because you have to reason about all the states where objects are either being grasped or not being grasped, and or are in stable configurations, and this has to be computed in a combination between all possible object and arm pairs, and also between arms for handoffs. And such a graphical structure for just two objects can be seen in the figure in the bottom right. And this underscores the importance that, especially when you have an increasing number of arms and an increasing number of objects, just naively searching that space is not going to be feasible or tractable. So now, what have we actually done in this work, and what are our contributions? So we show that there exists a structure in this problem space that we can leverage to solve these problems in an efficient fashion at the task level, in order to guide the task and motion planning search. So we show that the problem of synchronized multi-arm rearrangement is analogous to a multi-agent pathfinding problem on a graph under certain additional constraints. And to give a very brief idea about what that graph would be, so we reason about objects moving around different parts of the workspace under the imposition of staying in a stable placement area or moving via manipulation through robots. And over this graph, we want to make each object move in such a way that at any instant of time, a manipulator is constrained by the fact that it can only interact with one object at a time, and every stable surface is constrained by the number of total objects that it can admit on its surface area. Now, once we have formulated it as a multi-agent pathfinding problem, we can leverage previous work and modify it with extensions to formulate a mixed integer linear program to quickly find solutions to guide the search in the task planning space. And once we have this effective guidance, we incorporate it into a task and motion planning search tree that effectively explores these task transitions and picks these sequence of actions and computes the appropriate robotic motions to actually execute these actions. And we perform extensive studies and simulation where we push the class of problems that we can solve up to 9 robots and up to for 4 objects, and we consistently finds solutions within 10 seconds, even for such massive problem domains. Now, what is the mode graph with capacity constraints, which forms the basis of the key contribution of this work? So what we do is we create this graph where the nodes are either manipulators or placement regions, and each node has a capacity. So a manipulator has a capacity of 1 if we only allow a manipulator to interact with one object at a time. A placement region has a capacity of the number of objects that can be placed on it. And the edges between these nodes now become the actions that can allow the object to be moved from different parts of the workspace to other parts of the workspace. And the objects in this situation would be essentially agents or pebbles that are moving over this graph. And every valid motion of the object now maps to a sequence of edges or a sequence of actions that can approximate the solution in the task planning level. So let's look at the example that we had shown to be kind of non-trivial of just swapping two objects. So what does that look like? So for the two tables, we add the two nodes in the graph, let's say with capacity 2, and then we have the manipulators in the middle being two additional nodes, and the edges represent the valid actions that are possible given the reachability of the systems. So there are edges between the tables and each manipulator that is beside it, which either represent pick tasks or placement tasks. And there are edges between the manipulators themselves, which represent directional handoffs between the manipulators. And now, since these nodes have capacities, a valid solution that takes the object O1 from the left to the right and O2 from the right to the left needs to respect the capacities and also traverse the edges in such a way that the motions are valid. And this immediately expresses the fact that if you greedily, the problem that we described where greedy execution does not work here. So if you greedily make progress, you get stuck in the middle. So the solution, even at the abstraction of this object-centric graph, already shows that the task and motion planning solution needs to first address one of the objects, make it move to the other table, and then manipulate the second object. So just to illustrate the solution that would arise from this mode graph, you can see the steps would involve the object first being grasped from the left and then moving to the manipulator, which would translate into a pick action by the left manipulator. Then it's going to move to the second manipulator, which would be a handoff from the left manipulator to the right manipulator. The next step would be transferring the object from the right manipulator to the right table. And then the next set of steps can now transfer the red object from the right to the left. And once you solve this multi-agent pathfinding problem over the mode graph, you end up with a very nice heuristic in the task planning space, which already expresses promising actions that can solve the problem optimistically. Now it's up to a lower level search to figure out exactly how to compute grasps and placements and handoffs for the objects, as well as plan valid motions for each of these choices of actions. Now, in terms of the integer linear programming model for this abstract search. We leverage previous work which showed that there exists very efficient models which can map this problem to a multi-commodity network flow, which can be very efficiently solved. And we add, for the purposes of our work, an additional constraint to the model to encode the capacities, because the capacity is what is going to make sure that certain nodes can allow multiple objects or agents to occupy that node at different steps of time. So for instance, the tables in this example can allow two objects to coexist at steps, which is required for the solution. So once we have encoded this capacity constraint, we can add the costs to this model as heuristic estimates of what the cost of the corresponding actions would be. Now, if we want to merely minimize the number of steps or actions in the task, the cost can be encoded to be a constant. We can otherwise get the costs from some estimate of the motion planning execution time or distance. We can also approximate the cost from the workspace poses of these placement regions and manipulators. So using appropriate heuristics, we can also afford certain quality guarantees at the level of this search, in addition to promising feasibility guarantees in the task space. Now, we also added a modification on top of previous work, which guarantees that we will find a solution using a single call to the linear programming model. So previous work had the loop of calling it incrementally with changing horizons or number of steps that were allowed to admit the solution. What we did was to change the formulation such that we gave a very conservative estimate of the number of horizons that might be needed, and that allowed us to encode the solution as a set of necessary steps in the beginning and ending with a set of no action steps. And bringing this all together, once you have such a promising guide in the space of actions or in the task planning space, we can use it, use such a promising feasible task plan to now compute a feasible task and motion plans. So we need to now sample these transitions given a task plan. So what would these transitions be? So for every action, we need to compute the groundings for each action. So a pick action needs to compute grasping configurations, placement actions need to compute IK solutions for the placement, and handoffs correspondingly need to solve the IKs for both the arms and compute poses where the objects can be handed off. So in the space of the task and motion planning, we build a forward search tree to explore these different choices and keep growing the tree, and we allow alternative choices to exist. So ultimately, in order to maintain completeness, it is possible that you would have to explore a sequence of actions that are not recommended by your multi-agent pathfinding, or in other words, the multi-agent pathfinding over the mode graph identifies an efficiently solvable class of synchronized multi-arm rearrangement problems, where the mapping between the two problem domains work and act as an efficient guidance in this essentially complete search. So we perform experiments to compare our proposed algorithm, SMART, with alternative heuristics in the space of the task and motion planning search. So one such heuristic that has already been outlined is greedy, where we perform the sequence of tasks per object and we greedily bias it for every object to make progress. And then we also have a fallback where we solve the task plan for each object and then execute them in sequence. So the benchmarks we have chosen all involve KUKA manipulators, an increasing number of KUKA manipulators in a tabletop rearrangement workspace setup. And we evaluate three classes of tasks. One is to switch object poses between two ends of a table. The other one is to move a set of objects from one side to the other, and the third one being random, where the object poses are chosen at random and can involve a combination of switch and side-to-side benchmarks. So first, looking at the switch benchmark, we see that expectedly being greedy is not helpful, right? So the success ratio for greedy is very bad. And in terms of the computation time, we are better or competitive to like both the other baselines. And in terms of the solution cost, we are always going to be better than sequential, but are also in a lot of cases better than greedy. So now, of course, like executing things in a coordinated fashion introduces overheads of coordination. So we won't get the linear speed up because of this overhead. Now, in terms of the number of actions, we are clearly significantly better than sequential. Now, in the second benchmark, where the objects have to be moved from one side to the other, we again see the trend here that greedy now works because there is no bottleneck in the middle that is introduced. So everything succeeds. But the trend of the fact that we stay competitive with greedy but are better than sequential, both in terms of the solution cost as well as the number of action, persists. And in terms of even the computation time, we are competitive or beat the baselines. Now, the most compelling evidence comes from the random execution, where you have a situation where the objects have to move across arbitrary parts of the workspace. So we still maintain the computational benefits with regards to the competing methods, especially considering that we succeed all of the time. And when compared to sequential, we maintain cost benefits because we are definitely more efficient in terms of actions and maintain benefits in terms of the solution cost as well. And as you can see, we managed to push these benchmarks up to 9 robots and 4 objects. Now, for most of the problems that we have discussed so far, the objects poses were chosen to be in non-intersecting parts of the workspace, which kind of guaranteed monotonicity or the guarantee that the object only needs to be grasped once. We devised a very simple non-monotone example, as you can see in this video, where the objects have to be coordinated across 3 placement locations in such a way that an intermediate interaction is needed, right? Uh, so in such a situation, it turns out that our formulation is still sufficient to find these solutions. So a key and interesting feature here is we identified that it is indeed possible to also represent a subset of non-monotone problems using the abstraction of multi-agent pathfinding over our mode graph construction. And even in such problems, we find solutions very quickly. So just to summarize, we proposed a method to address synchronized multi-arm rearrangement problems, and we mapped such a class of such problems to efficient multi-agent pathfinding over mode graphs with capacity constraints. And using this mapping, we can effectively guide the search in the domain of task and motion planning uh, to find solutions for a large number of robots and a large number of objects very quickly. And I would encourage the viewer or the listener to visit our paper and refer to the details therein. Thank you.